All right, so we've got this from set number 13. It's number 3. It's applying the principle of impulse and momentum. So we've got 3 identical spheres, A, B, and C, so the mass is the same. They slide freely on a frictionless horizontal surface. So that means their weight is not in the plane of motion, so that's not going to affect the motion. They're connected by these inextensible, inelastic cords to the small ring at D, which is massless, and D is the mass center. The length between D, B is L, and that's also the length between D and A, and this length here is equal to 2L cosine theta, which basically makes D the mass center. Okay, so they could have asked you to calculate this length if they gave you that D was the mass center, but they actually thought, oh, this problem's hard enough, we won't make them calculate that. So initially the spheres are rotating about the ring D, which is at rest, at speeds proportional to their distance. So both A and B are going at the speed v0 initially. And we'll have to calculate what C is doing, but we can do that because it's proportional to the distance. I'll just put it right now as VC0. And they tell us that this angle theta is 30 degrees. Suddenly the chord CD breaks. Okay, so this is just rotating around D, okay? D is not moving, these balls are rotating about D with these velocities. And, you know, the picture that you were given for this problem kind of had it at an angle, and I just decided I didn't like the angle, and so I put it like this. It doesn't really make any difference to the problem, but it makes it just easier to look at and think about. So C is out of the picture, because if it breaks when it's in this position, C is just going to continue going up, right? There's nothing to, you know, really once this chord breaks, there's no forces acting on C, at least in the plane, you know, there's the weight and then the normal force of the surface, but in the plane of motion, there's no forces, it's frictionless, so it's just going to go off forever. Same for A and B, they're going to go off in their respective directions, but there's a catch. There's a rope between them attached, or a cord, attached to ring D, and at some point, that cord is going to become taut. And when it becomes taut, we're asked to find the velocity of D and the velocity, the relative velocity that A and B will be relative to D. Wow. So that's what we're looking for. And then part C, the percentage of energy of the original system which dissipated, that's actually just a matter of calculating the kinetic energies. And once you have the velocities, that's pretty straightforward. So I'm actually not going to do that part of the problem. All right. So who's got some ideas here? You solved this problem at one time, right? What's that?
Use the coordinate system.
Okay, sure. Which coordinate system? Maybe call that X
The plane motion works.
and that Y?
Yeah.
All right. Now what?
Sketch the picture before and after using the impulse momentum theorem.
Okay, well, we are definitely going to be using impulse and momentum. And maybe even do the angular momentum as well.
You do have to find C, right?
What do you mean?
Oh, VC. Or is that not?
Oh, yeah. Yeah. You know, I don't want to take the time to do that. I mean, it's just 2v0 cosine theta. I mean, it's just a proportionality. VCO is to 2L cosine theta as V0 is to L, right? Because they say that it's proportional to the distance. All right. So what do we notice about this problem? Okay, so first of all, so I'm using, I kind of have this intuition that I'm going to use the principle of impulse and momentum because we are talking about like some time intervals here. It's like first the cord breaks and then sometime later the cord or the string is going to become taut. So, yeah, I don't know how else to motivate it, but the thing about the principle of impulse and momentum is that once this cord breaks, what forces are acting on these, what external forces are acting on these balls?
Tensions to unbroken cord.
Well, that's not even going to be in play until this is taut. And even once it's taut, that's going to be an internal force. It's going to be a force between the ball A and B. It's not an external force to the system. So the answer is there are no external forces acting. So in both of these equations, the impulse and the angular impulse are zero because there's no external forces. So basically the bottom line is linear momentum and angular momentum are conserved. Once you get that, the rest is easy. Well, maybe not easy, but... Because what we can do is we can calculate the linear momentum, and by the way, for the principle of impulse and momentum, these subscripts refer to time.
Is there also a mass on D? Or is that
No, I think they said it was a massless ring. So, it is a ring, but there's no mass. Okay, so both linear momentum and angular momentum are conserved. We're going to use the linear momentum to get VD, and we're going to use angular momentum to get these two. And we're going to use the calculation for linear momentum. There's two versions. There's two formulas that we can use for linear momentum. And there's also two, again, if you go to this chart, you can see for linear momentum, in fact, it's the first row. If you have a system of particles, which we do, right? We've originally got 3, but once the cord is cut, I really only want to consider the system of A and B. So I can do it separately by just calculating the linear momentum of A plus the linear momentum of B, or I could calculate the linear momentum of the system, the total mass of the system times the velocity of its mass center. So I'm going to do it both ways. And then similarly for angular momentum, there's 2 different formulas that you can use, and we're going to use one formula for the time t equals 1 and a different formula for the time t equals 2. They have to be equal to each other because it's conserved and it all just kind of falls out. Okay, so let's do it. So first let me identify. T1 is the instant just after cord breaks. Okay? And then T2 is the instant just after cord becomes taut. All right, so now that I know exactly what the subscript 1 means, I can go ahead and calculate the linear momentum for time 1. Okay, so it's just mv, right? And we've got 2 particles, so I've got to add them all up. So it's mv0 plus mv0b, and so these are vectors. Notice though that the x component here is going to cancel out the x component here. So really, it's just going to, and the y components are going to be the same, so it's just going to be 2 times the y component. So it's going to be 2m v0 cosine. So that's L1, and it's in the minus j direction. Okay, so let me give you a minute. Should we cut?